Hello everyone, myself Sachin. In this video, we are going to discuss about rings, integral domains and fields. If we talk about the group or semi-group, then we have set with one binary operator. When we talk about rings, integral domain and fields, here we have set with two binary operators. If we talk about the ring, then ring is consist of abelian group under plus and semi group under multiply. Further distributive property is added. This concept is called ring. If we talk about the commutative ring, in the ring, commutative property under multiply is added. If we talk about the integral domain, further multiplicative identity and no zero divisor is added in the commutative ring. Then this concept is called integral domain. If we talk about the field, then further here multiplicative inverse is added in integral domain. Then this concept is called field. If you are new to our channel, please subscribe the channel. Also like, share and comment the video. Initially, we are discussing about no zero divisors and without zero divisors. Say here we have two elements. Elements are A and B, and these elements A or B are the part of the ring. And these two elements are A and B are equals to not zero. I mean these elements are non-zero, but AB equals to 0. Then A and B are called here zero divisors. For example, we have here Z6. Z6 means here we have numbers 0 to 5 and we are applying here modulo division 6. I mean we are getting here remainder if number is divided by 6. Therefore, remainders are here 0 to 5. In the Z6, we have the numbers from 0 to 5 and we are using the concept of modulo divisor. I mean number is divided by 6. Say we have here numbers 2 and 3. These 2 and 3 are multiply each other. Number is 6. And now this 6 is divided by 6. Remainder is 0. Therefore, we are writing 2.3 equals to 0 under mode 6. We can say that 2 and 3 are 0 divisors because 2 and 3 are non-zero values, but 2.3 equals to 0. Therefore, 2 and 3 are here 0 divisors. If we talk about the no zero divisors, say AB equals to 0, it simple means either A should be 0 or B should be 0. Then A and B are called here no zero divisors or without zero divisors. If we talk about the examples, say we have here set Z and we have here plus operator and multiply operator. We are studying here various properties because with the help of these properties we can prove whether this is field, ring or domain, integral domain. First property is here closure. Initially we are studying plus operator. Then under the plus operator, closure property is true because 2 and 3 both are the part of the integer and we apply the plus, then further we get here 5 and this 5 belongs to integer. Therefore, closure property is satisfied. If we talk about the associative property, as we know that under plus operator, associative property is true. I mean 2 plus 3 plus 6 equals to 2 plus 3 plus 6. Both are the equals because we are getting here same value. And if we talk about the identity property, then under the plus operator, identity is 0 and this 0 is part of the integer. Therefore, identity property is true. If we talk about the inverse, then inverse of 2 is minus 2 because 2 minus 2 equals to 0. I mean we are getting the identity. Therefore, minus 2 is the inverse of 2 and this minus 2 belongs to set of integer. Therefore, inverse is available. If we talk about the commutative property, then we can write 2 plus 3 equals to 3 plus 2. I mean all 5 properties are true here. Therefore, abelian group is formed. If we talk about say here Now next our operator is here multiply, because we have to study multiply also. We can write 2 multiply by 3 equals to 6, and further this 6 is part of integer. I mean closure property is true under multiply. Further, associative property is true under multiply. In both the cases, same value we are getting here. If we talk about identity, then identity is here 1. Multiplicative identity is always 1. And this 1 belongs to integer. Therefore, identity is available. If we talk about the inverse of 2, then inverse of 2 is 1 by 2. And this 1 by 2 does not part of the set of integer. Therefore, inverse property is not available. If we talk about the commutative property under multiply, then 2 multiply 3 equals 2. We can write 3 equals to 2. Commutative property is true. And further, if we talk about the integer and plus or multiply operation, then distributive property is also true. Therefore, we can say that this particular combination, this particular set under plus and multiply is ring, because abelian group is formed. And we have here commutative ring, because closure property, associative property, I mean semi-group property is true. Further, commutative property is true. Therefore, we can say that commutative property is true. Commutative ring is true here. And integral domain, if we add identity in the commutative ring, then this concept is called integral domain. Identity property is true under multiply. So therefore, this examples belongs to ring, commutative ring, and integral domain. If we talk about the next example, say set of real numbers, and we have here further these two operators plus and multiply. Initially, we are discussing about closure property. Say numbers, further we are taking 2 and 3, and under the plus result is 5, and this 5 belongs to set of real numbers. I mean closure property is true. Further, associative property is true, because associative means here 2 plus 3 plus 4 and 2 plus 3 plus 4, both the values are the same. Therefore, associative property is true. If we talk about the identity, in case of the plus, identity is always 0, and 0 further belongs to set of integer. We can say that identity property is true. If we talk about the inverse, under the plus, further inverse is minus 2, and if number is 2, then this minus 2 belongs to set of real numbers, and we can say that commutative property, I mean inverse property is true. If we talk about the inverse, then 2 plus 3 equals to 3 plus 2. Therefore, this is here abelian group. I mean under the plus, closure, associative, identity, inverse, and commutative properties are true. If we talk about the multiply operator, further we can write say two numbers, 2 multiplied by 3, this is 6, and 6 is the part of real number. Therefore, closure property is true under multiply. If we talk about the associative property, then we have 2 multiplied by 3 multiplied by 4 equals to 2 multiplied by 3 multiplied by 4. Both the values are the same. Therefore, associative property is true. If we talk about the identity property, then the identity of multiply is 1, and this 1 is belongs to set of real numbers. Further, we can say that identity property is true. Now, if we talk about the inverse property, then inverse of 2 is 1 by 2, because if we multiply 2 by 1 by 2, then number is 1, 1 is here identity. Therefore, 1 by 2 is the inverse of 2, and this 1 by 2 belongs to set of real number, I mean inverse is available. If we talk about commutative property, then we can write 2 multiplied by 3 equals to 3 by 2. I mean this is also true. So under the plus we have seen this is the abelian group. Under the multiply, closure is true, associative is true, therefore this is the ring. Further, commutative property is added, then this is here commutative ring. In the commutative ring, identity property is added, then this is the integral domain. And in the identity property, inverse is added, therefore this is the field. In this way, we can find out particular algebraic structure is ring, commutative ring, integral domain, or fields. thanking you.